Okay, so yeah, this is where we left off last time. Download the CSV file, write a function to load airports. And so here's what I did. Let's see. I load airport data, I gave it the file name. I opened the file, called whatever file name is. I did it as a CSV reader. I created an empty list of airports, and then for each row in the CSV file, append to the list of airports that row. Close the file when I'm done, and return the airports list. So, if we run this, oh, what did I do wrong? Oh, I gotta upload the file. Upload airports, perfect. Let's try this. There we go, worked this time. And do this, and yep, there we go. We see airport code, and then it's just a list of lists. Great. So we loaded all the data in. And now for something not so much about the loading the data, but write a function getName from code that will return a string containing the full name of the airport with the corresponding airport code. The parameter airport list should be the list. Yeah, okay. So write a function. Here. Okay. So I'm going to go down here. Def getName. So look, I have a list of lists where the outside list is just the list of airports. And each airport is represented by a list where the index 0 of that list is its airport code. And the index 1 of that list is, well, the actual name of the airport. So what I have to do is this function is going to take the airport code, maybe like, what was Halifax? YHX or something? Z? Okay, perfect. Did you say Z? What the hell is Z? So YHZ is Halifax. So if I gave this function YHZ, I'm going to have to do a search through the outside list and look at index 0 of each internal list to see does it match YHZ. So I just need a linear search. Great. For in airport list. So airport list in this scenario is my haystack, and the airport code is the thing I'm looking for. That's the needle. So for each airport in the airport list. So what this is going to do, this is a for loop, and each time through the loop, airport will be that sublist. That list representing the airport, where index 0 is its code, and index 1 is its string. So I'm going to search through this. So I need to check if airport at index 0 so that would be that list of the airport, index 0, your code. Does your code match the code I'm looking for? Air potty. Great. What do I do if it matches?
You return the airport at 1, index 1.
Bingo. Return at index 1, because I don't know why that's happening. Return airport at index 1, because, well, if airport at index 0 is the code, airport at index 1 is its name, based on how we defined how this information was represented. And then what should I do if I ever get to the end and don't find it? What do we think? Return -1? Sure. Now, maybe -1 isn't a great choice in this particular scenario, because this function should be returning a string, right? And so the -1, which is that sentinel value that we care about, it's not a string. So this function is very explicitly maybe not returning the string. So maybe I would do like not something to be very clearly like, I didn't find it. Great. So we run it, okay, and now let's test it out. Print, what the hell? Equals get name from code. I give it YHZ and airport list of airports. And then print Halifax Stanfield International Airport. Perfect. It worked. I mean, this time it was kind of interesting because before we did our linear searches where it was tell me if it's there or not. All right, so you find me search for it. And then we did ones where it was, okay, don't just tell me if it's there or not. Tell me which index it's in if it's there. All right, so that was the modified linear search. Now this linear search is a little bit different because find what we're looking for, but then return different related information. Right, so we did a search based on some value, but then the thing that I actually cared about was its partnered other value, which just FYI, right? It's a little different, but it's still just a linear search. Linear searches are everywhere. So great. Now I want to see real quick here, Python, time, code. I want to know if there's like a really quick and easy way I can do this. Come on, I just want a simple answer. For time, time. Is it time.perf counter? I'm gonna do a real quick check to see if I can get this to work. If I can, great. If not, it's really not that important. I don't know what perf counter is. And then, is it a function call? Perf, what do you, 367? Probably nanoseconds? Okay, there we go, cool. All right, so yeah, let's, here's what I'm going to do. Start time. Nope. So what I want to do is I want to measure how long this took. Print end time minus start. There. Isn't that really right? Nanosecond, millisecond. What is nanoseconds? Time 10 to negative 6 or not negative 9? 9? Okay, so 1, 2, 3, 4, 5, 6, 7. Okay, so this took like 2 milliseconds, it looks like, right? 2 milliseconds, not very long. It's weird that when I'm running it's taking like wildly different times, but this is just an experiment I'm doing. I'm curious if it's going to work. So here we did the linear search, but I do have a little thing here. If your function made use of a linear search, can you think of a way to alter get name from code and load airports such that you do not need a linear search? Does anyone have any ideas? How can I do this without a linear search? Dictionary. It's a great idea. How about, instead of loading the data into a list of lists, we just load it into a dictionary where the key is the airport code and the value is its corresponding string. Seems like a good idea? Yeah? No? Yeah. So, let's take a second and be like, okay, this is like 2 milliseconds, it looks like. 1, 2, 3, 1, 2, 3, yeah, 2 milliseconds. I'm gonna go here and I'm gonna change this load, and instead of putting it into a dictionary, I'm gonna make an empty dictionary, pardon me, instead of putting it into a list, I'm gonna put it into a dictionary. So I'm starting with an empty dictionary. Then I'm just gonna keep adding to the dictionary. So I'll say airports at index row 0, because row at index 0 is the airport code, right? So I'm going to say row at index 0, that's your airport code. So you're the key. At that key, have the value row at index 1. And then here, there. We're not returning a string anymore, we're returning a dictionary. So now, when I run this, list of airports, it shouldn't be list. I'll keep calling it list because I'm lazy. But now, list of airports is actually a dictionary. So run, and now we can see, I mean, we've got the braces, the squiggly brackets. And we see like ABE, the key, and then the associated value is Allentown, Bethlehem, ABQ, Albuquerque International, AGC, Pittsburgh, Allegheny County, AIY, Atlantic City International, and so on. So now we have key value pairs. So now, for my get name from code, I can just do like return at index airport code. That's it. No need for the linear search anymore. Be like, okay, dictionary, here's the key, the thing I'm looking for, the code. Just give me the corresponding value, which this would do. I'm indexing the dictionary with the key I care about, the airport code. So I hit run, and now let's run again. And it still works. Great, right? There. Now I'm curious, shoot, it's the print that would have taken so long. Shoot, I wish I didn't do that. Yeah, shoot. I bet if I do it this way. Yeah, 1, 2, 3, shoot. Okay, I need to go back in time to make this back to a list. And then run. Okay, it's back to a list, and then this is going to go back to what it was, the linear search. It still works. So notice that when I did it with the dictionary, it took 82,000, almost 83,000 nanoseconds, which is a very tiny amount of time. Curious how long it'll take if I do it with the lists. 99, so not a huge difference. But measuring how much work and how much time a computer is taking to do something, just taking a time difference is a terrible way to do it because computers are always doing a bunch of other processes at the same time. This was just a quick and dirty way where I wanted to see, like, is it going to be fat? Like, can I measure the difference in the amount of time it's going to take? If the list of airports was bigger, I'm betting, oh, look at that. Oh no, that was, look, 120,000, 217,000, 106,000, 159,000, 188,000. What was it before? Almost 83,000? But we're seeing with the list, it's definitely taking longer. 95,000, that was not too bad. 121, 122, 151. This is a terrible way to measure the amount of time, but with the dictionary, I'm not doing a linear search. The amount of time my algorithm is going to need to do a lookup in a dictionary is the same, whether that list is size 100 or a million. But if I'm doing a linear search, what takes longer to search through? A list of size 100 or a list of size a million? A million, right? But with the dictionary, it's not going to make a difference how big it is. With the linear search, it's going to take longer and longer the bigger it is. So an optimization in this particular scenario would be maybe start not as a list of lists, as a dictionary. I saw a hand up there. Yes? No, because the time it takes online is, I tell it to run remotely. It does the calculation and counts the time and then just sends it back to me after it's done everything. But your head's in the right place of like, well, you know, are there a bunch of other variables here that can affect how long it's... Yes, absolutely yes. This is a terrible way to measure performance of code. Because maybe at that moment Colab was also, like the computer that was doing, was also checking for updates at the same time. I don't know, right? So there's that. We don't need a linear search if we use the dictionary. Great. Any questions about what I just did? Yes?
If the thing that you're looking for in the linear search is further to the start in the list, will it take less time, or does the linear search still have to search the whole list?
Though it'll depend on how it's written. With the way we wrote it, we said as soon as you find it, return, right? So you're right. A very good observation. If I have a list of size 1 billion, and I'm looking for the letter A, and I look at the index 0 of that list, and it's an A, how many things do I have to look at to find it? Just the first of the one, right? So obviously it's going to take less time. The trouble is, you know, for every time the thing you're looking for is at index 0, there's going to be a time you might be looking for something at index, like n minus 1. For every time you find something at index 1, there's going to be one at index n minus 2. So on average, how much work, on average, here's a thought question for you, and it's fine if you don't know. On average, how many things would you have to look at? If I were to run this linear search on a list of size 100, on a list of size 100, on randomly selected things in the list that I could find, right? So let's say I'm doing the linear search on airport codes. I'm going to look for Albuquerque, then Halifax, and then this, and then this. So all over the place. There's no pattern to how I'm looking for things. I'm just going to run this linear search 100, a million, a billion times. On average, how many things will I have to look at each time on average? 50. Half of them, right? Because on average, it's going to be like the middle of the list, right? Because for every time it's at index 1, it's at index n minus, or index 0, it's at index n minus 1. Index 1, n minus 2. Index 2, n minus 3. And so on and so on and so on. So it always gets kind of like averaged out. So good observation. And in reality, on average, it'll take n over 2 amount of work. But an interesting thing that we will talk about eventually, an interesting thing, when we talk about how much work an algorithm is going to do, we don't care about coefficients. In this case, it's like 1/2 times n. That 1/2, that scalar, that thing that scales the amount of work being done, I don't really care that much about it. Because we're talking about these like big different categories of how much work the computer's going to need to do. The point is, if I had a list of size 100, and you know on average that I'm going to have to look at 50 things, if I double the input size, how many things, like what happens to the number of things I'm going to have to look at on average?
It'll double.
It'll also double. So the point, the reason we don't care about the coefficient, it's because we care about how does the amount of work grow as we make n bigger. And the amount of work, sure, the total amount of work is like on average n over 2. But the point is, as n grows, the amount this grows is linear. You double the input size, you double the amount of work. You quadruple the input size, you quadruple the amount of work. It's kind of interesting things to think about, but these are topics that we're going to talk about later. Great, you can write to CSVs as well with something like this. Open, CSV writer, CSV write row, first cell, second cell, third cell, and so on. And of course, at the end of this, what is this piece of code missing right here? Close, right? So here's hoping that there's a lot more code in this that that I just didn't show because forgetting to close it, should probably do that. Here's a good PR for anyone who wants to do something on the GitHub. Go add that real quick. You can totally do it and submit a pull request to just say outfile.close at the end. That'd be a good PR. You'd get a big thumbs up from me if you did. PR pull request. So you can write to CSVs. The takeaway of that topic, talking about file input and file output, is not that you leave this lecture hall going, I know exactly how to input from a file to Python. No. It's that you leave this lecture hall and you go, okay, I know that I can do that. And I know I have the requisite skills to be able to go to Google and say, load file in Python, and go, oh yeah, there it is. Or at least come back to that page and reference it for when you need to use it. No programmer in the world, you'd have to be crazy to, no programmer in the world would sit here and maybe someone in this room is going to somehow become the most effective, best programmer ever in the history of the universe. Maybe. But even if you're in this room, I guarantee you, you will not, when you become that best programmer in the world, and I said, input the file in Python, you're going to be like, okay, how do I do that again? Because you just don't memorize that stuff. Something like this, maybe you might end up memorizing if you do it enough. But in general, we're getting to the point of the course where, sure, you've memorized, you know how variable works, you know how to make functions, and all those different things. There's an amount of stuff you just need to know. But we've kind of covered all that now. There's one big last thing we need to know is objects. Everything else from there is, hey, this exists. Maybe you'll use it on an assignment in this class, maybe you won't. But no one expects you to leave this lecture hall knowing absolutely everything about that thing. It's not going to happen. No programmers are like that. No one does it like that. And if you're expecting that to happen, you're going to be very disappointed. The point is, everything we learn, you're aware of it, so when you need it, you can do it. Yes?
Does that mean there would be something about opening up a file on the exam?
It could be there, but you got to know that, on an exam, there probably won't be something specific like that, okay? But on an exam, if I did have a question like open a file, and you're like, oh shit, I don't remember how to do that in Python exactly, and you just wrote somehow open file, right? I'd go like, yeah, they know that you need to open file, right? When the exam's getting marked, it's marked in a way where I'm measuring your understanding, not, oh, you got the syntax slightly wrong there, that's no good. No, that doesn't matter. It's about, can I tell that you know what a linear search is, Yeah. If you're not wearing a mask, put it on, just in general. Exceptions. Who here has ever seen something like this before? Put up your hand. Of course you have. Where you see Python go value error. You're telling me to turn the string hello into an integer? That's not a thing. Or how about this? Here is a list, A, E, I, O, U. Give me the thing at index 11. And then you see index error. There's no thing at index 11. You ever see something similar to that before? Of course you have. Both value error and index error are what we call exceptions. Now, there is a lot we could get into when talking about exceptions. We're going to scratch the surface, and you need to get the spirit of what exceptions are. That's what's important. But in the above example, we tried to access the 11th thing in that list, but there's only 5 things. So Python raised an exception. Raise exception is a very important keyword concept. When you see an exception, whenever you see something like index error, value error, an exception was raised. Now, exceptions, at this stage, the exceptions you've seen have all been bugs, errors. But an exception really isn't about errors. It's about exceptional situations, right? Here's operation of a list. But you know, someone might try to index something that doesn't exist, and that's kind of a funny situation. So we're going to raise an exception. So it tells the programmer, okay, something funny happened. Something exceptional, something unusual happened. So it's not necessarily an error, the spirit of exceptions. It's not that they're necessarily errors. It's just something interesting happened. Something funny happened. Or something funny could happen. So Python knows to raise an exception when something funny happens. Consider how print function, great, yeah. Someone had to write the print function eventually. They probably wrote it something like 20, 30 years ago, right? Someone had to write the code for converting strings to integers and indexing elements. What? Consider how, like, the print function, someone had to write the code for converting, oh, perfect. Yes, someone wrote the function for print. Someone also wrote the code for indexing lists, right? That's code written in Python to tell Python how someone indexes lists. How do I do that? There's code for that. Someone wrote the code for converting integers to strings, or strings to integers. Someone wrote that code. Someone had to write that code. But someone wrote that code. If you're going to pay attention to anything in this topic, it's this. I'm writing the code for converting strings to integers, right? And it's 1994, okay? And I'm sitting in my office and I'm writing that code that everyone in the future is going to be using in Python. So I'm writing that code then. And then you, in the year 2022, comes along and you write something like int hello, right? Something funny happened. You tried to convert the string hello to an integer, which isn't really enough. But me, as the programmer, in 1994, is that what I said, 94? Whatever, in the 90s. What do you want to do about a situation where maybe the code tried to convert the string hello to an integer? Because maybe what happened was you asked a user for input. Give me 2 integers. And they wrote hello, right? They hit enter, and then you see this exception. So what happened here, if that's the scenario, there was a user error. It wasn't really the programmer's error at that point. The programmer said, give me the 2 integers that you want. I know they're going to be strings, so I need to convert them to integers. But the user blew it. The user wrote in the string hello. They didn't give me integers. You can't convert the string hello to an integer. You can't. So I'm going to ask you, what do you want to do about that situation? You today, what do you want to do about that situation? Well, maybe if that happens, you just ask the user, like, no, you messed up, try again. Or maybe you just want to, like, whatever, they're a moron, ignore it, carry on. We don't want the whole program to crash, just ignore that issue, carry on, the user's a moron. Or maybe you want, like, immediately stop running, this is critical error, we have the nuclear fuel rod on the rocket that's taking us to the moon, and someone entered hello, and that's something bad. We're going to abort, right? Maybe that's what you want to do today. But here I am in 1994 writing the code. And I'm faced with a decision. Someone might give me a string that can't convert. So what do I do about it? Well, you're the one that's going to be using my code in the future. So the question is not, what am I going to do about it? The question is, what is the future programmer going to want to do about it? And the answer is, how the hell do I know? That's going to depend on what you're using it for. So here's what I can do, is I can raise an exception to let you know, the programmer in the year 2022, that you're using my code from 1994 and something funny happened. Something exceptional happened. I don't know what you want to do about it, but here's an exception. Now you have to deal with it. It's your job to say, what am I going to do when this happens? That's the point of exceptions, is it gives me a way to literally communicate to you in the future, something funny happened and you have to do something about it. It's not my problem, it's your problem. Because how could I know if you want your code to abort? How do I know if you want your code to just ignore the problem or keep prompting them for input? I don't know that. So the best I can do is raise an exception, say, oh, something funny happened, you have to deal with this situation. That's what's going to happen. That's the spirit of exceptions. It's a way to communicate information to the future, and the information being communicated, like a function takes input, produces output, right? And let's assume it's a pure function. Takes input, produces output, that's it. But when something funny happens, it's like the function needs to have like a, uh-oh. It's got like another way of communicating information. Here's my function. It takes input, produces output. I give it hello. It can't give me output. So it has this like third secret way to be like, something funny happened, deal with it. It gives me a way to pass information around, and the way that the information is passed around is separated from the normal logic of your code. The normal logic of the code is this, right? Function input, function output. But when something funny happens, we need like a new way to be like, okay, we're separating this logically, the exceptional situations and the normal functionality. So I just ranted a bit, and I think this is going to get more obvious if we see an example. Let's say I'm writing a function in 1990 whatever. It's called divide. It takes A and B, but of course, we all know that you can't divide by 0. That's a problem. All right? So, what I will do when I write my code today is I can say, all right, if B is 0, is the divisor 0? That's what you call the thing on the bottom, right? Divisor? Denominator? Well, that's if you think of it as a fraction, right? Whatever. The number B. If B is 0, let's just go with that. If B is 0, my function is going to raise an exception. Because you can't do that. That is not normal operation of divide. Okay? You can't do that. On any other situation, I'll just do divide. Right? Any other situation, I'll just do A divided by B. But if it just so happens that someone gives me a 0, that means someone used this function in a way that they probably shouldn't. But whoever's using this function, I don't know what they want to do about that. Was that just a dumb bug they need to fix? Or was this possibly something that happened? Imagine for a second maybe this code is running on a computer that has a bunch of sensors that measures various different things. And maybe periodically it could just so happen that that sensor, the value it reads was 0 because it was so small, but it really wasn't 0. So what do you want to do in that situation? Maybe it's an entirely meaningless thing. Maybe it's really important. I don't know. But I don't know what you want to do about it. If you're using this function, I will do the division just fine. I'll be happy to do the division unless you give me a B of 0. Then I go, whoa, can't do it. Raise the exception. Your problem, not mine. What do you want to do about this? Because how do I know what you want to do about it in 1990, in the 90s, 94, whatever year I used? How do I know what you want to do if someone passes a 0? If you accidentally pass a 0 here, or maybe you intentionally did it, I don't know what you want to do about that. All best I can do is just be like, something funny happened, something exceptional happened, someone's got to look into this. That's what this is all about. So divide. If B is 0, raise an exception. Now here you will see 0 division exception, or 0 division error. There are a lot of errors out there, like value error, index error. There are a lot. They exist in Python. You can actually make your own types if you really wanted, but we don't need to. When writing code that you want to raise an exception, you choose an exception type that just makes sense in this situation. It just so happens there exists an exception type called a 0 division error, so I used that. And then it allows me to give it a string there as well if I want to provide additional information about what actually happened or whatever I want. So let's see what happens. I'm going to take this. I'm going to go, let's just go down here. One divided by 2. What? What did I do wrong? No. Yikes. There, 1 divided by 2. Great. 1 divided by 3. Great. 1 divided by 0. We have a 0 division error. 0 division error, that's illegal. That's what would happen. Okay? That is raising the exception. Raising the exception is bringing to the attention something funny happened. The other half of this is, well, how do we dictate what to do about this exceptional situation? Okay. All right. Catching exceptions. So pretend the above function was written in 91. You're using it today, you end up calling divide 9 0. Somehow, maybe you read input from the user and they entered a 9 and a 0, something went funny. Who knows, but somehow your code ended up calling this function such that b was 0. What should the original program in 1991 do about the situation when you accidentally gave me a 0? Well, not much, considering you're the one using the function in the future. I don't know. I might be dead, I don't know. How could the programmer know how to handle your specific situation today if the programmer's from 1991? Right? So what the original programmer can do is add some special code that says something exceptional happened, they raise the exception. Then you, the programmer, this allows you to use divide today, and then if that exceptional situation happens, you get to write the code to tell Python what to do if this happens. Because what do you want to do? Do you want your program to immediately crash? Maybe. Maybe it's really important that your code doesn't keep operating if a 0 got passed for whatever reason. Maybe you want to tell the user that they're a moron and that they can just please give me better data, b can't be 0. Maybe that's what you want to do. Maybe you want to just entirely ignore it. Great, something exceptional happened. I acknowledge that, but it doesn't matter. I can carry on. Great. Whatever. So if you're using the function, what you would say is try to do this. Try to run this code that might raise an exception. This is if we have an exception that we would call as like catchable, in that it's an exception you might want to catch. There are certain types of exceptions that you don't really want to catch. It usually is like, no, it's a bug. For example, you're indexing things that aren't there. Whatever. We say, try to run this code, but the code that is in that try block, we write try colon indent, like everything else in Python. The code that's in there is the code that might cause exceptions. Then we say, except whatever error, whatever exception type might get thrown. Then in this block, I write, what am I going to do about it? If this code runs and no exception is thrown, no exception is raised, we skip this. We just carry on as if everything's normal. If it does raise an exception, rerun this special code that is the exceptional scenario code. By the way, you may have been hearing me say things like throw exception instead of raise. In other languages, they call it throwing exceptions. So you will hear programmers interchange throw and raise often, FYI. But we're raising the exception in Python. So the code in the try would be something that may cause an exception. If it turns out that the code does raise an exception, the code in the except block runs. If no exception arises, the except block is skipped. It's kind of like an if statement that only checks for exceptions. This except is like, if the exception happened, do this. But it's not an if statement because, well, this is the separate exceptional situation type of code we write. Any questions so far? What have we learned? Code can raise an exception. You've seen exceptions raised, meaning some code you've used, whether you realize it or not, has some code in it that says raise index error. We also saw that, well, you could write your own function and specifically say, okay, raise an error if something happened, the divide by zero example. And now we're talking about okay, what are we going to do about it? How do we catch the exception? How do we manage it? So, for example, you know what? Here's what we could do. Here's one solution. There is, by the way, a special value for a float. You know, floats have all these different values. It could be 0, it could be 1, it could be 1.01, it could be 0.33333147, whatever. And have all these special values. But there's also this other very special value that a number can have, and it's called not a number. So a float can have the value not a number, which is, it's a special value that the float can have. It's a type float, but it has a special meaning, and it means that when something funny happens, it's not really a number. So in this situation, what I can say is, all right, if you try to divide something by 0, what I will do is I will just be like, okay, the result of that is not a number. And then I'll carry on. That's what I'll do. So, A, B, great. I try to divide A and B. And then if it happens that zero division error was found, if a zero division error was raised, what I will do is I'll say, okay, quotient, just be not a number. Take on that value, you're a float, take on the value though, not a number for a float, and then return that value. That's what I want to do if in this situation. This is a reasonable thing to do in this situation. This is a great idea. If someone tries to divide by 0, just return not a number. And let me just show you. A equals float, nan, print A. Print type of A. Missing a parenthesis. So, we can see I printed out A, it's not a number, but its class is it's a float. So just showing you this is really an actual thing. Great. So if divide is called and there's no zero division error, it just carries on. If divide is called and there is a zero division error, well then we'll just say, okay, the answer is not a number, return not a number. Cool. Here's another example. Because remember, I don't know how the programmer is using my divide function. So maybe you're a programmer and you're writing some code where you want to continually prompt the user for input until they do the input right. Because you know users are assholes and they're always going to try to break your code. So here's what I'm going to do. Here's my code. I say, okay, while true, so I want an infinite loop. This just means keep. So while true, read some input, split the data, extract it A, B. Great, I now have my A and B. So the user gave me input for A and B. I try to divide it. If I see the zero division error, I just print out cannot divide by 0, try again. Maybe I should have said try again, asshole, or something, because you know they're trying to break it. Just try again. So this finishes, and oh, well, the loop just ends, and it'll just keep looping. It's not unless we call divide, quotient goes there, it hasn't raised an exception, it can then go to the following line of code, and we see break. Raise your hand if you've seen break yet. A couple people. Break is a special keyword statement in Python that means, and other programming languages, that means exit the loop right now. So this is a way of saying loop forever, but if you get the input that you do like, if everything works normally, exit the loop. If something funny happened, print to them something they can't divide by 0, try again, and then the loop will just repeat. So in this situation, the programmer wanted it so, well, don't return not a number. What I want you to do is just keep prompting them until the input's correct. Why? Because that's what they wanted to do. Here's a third example. Maybe you have some very important medical equipment that is applying radiation therapy to someone. And for whatever reason, somehow, it got bad input. And if it gets bad input, you do not want this radiation therapy thing spamming radiation out to people. Because remember, what happens as the thing you divide by gets smaller and smaller and smaller and smaller and smaller? The result gets bigger and bigger and bigger. So maybe it was a calculation to divide how much radiation, and suddenly it's 0, so is it going to be like, oh, it's infinity. Give it infinity radiation. I don't know. Something bad can happen. So if this calculation starts to happen, and it gets bad input, immediately stop. Abort, crash, stop. There's a function called exit. That means stop. It'll tell Python, immediately stop running. And I'll show you, if I go down here, so everything's running, if I call exit, and I run it, it's going to start saying, why did it not, there. Your session crashed for some unknown reason. Well, I know why. I told it to. But maybe immediately stop. Or maybe it really doesn't matter. Maybe the exception got raised. It got raised, so if I see it, I just say, carry it. Pass, remember, is a keyword statement that says, shut up, keep going, ignore me. So this is like you as the programmer saying, I acknowledge that the exception existed, and what I'm doing about it is I want you to ignore it. Because if you didn't explicitly say, I want to ignore it, the exception will crash the program, right? Because you saw it said, remember, if I go back, you'll see, when I ran this code right here, I tried to divide by 0, it crashed the program. So when I say except this exception and pass, that means, okay, yes, I'm taking it, but I'm just deliberately ignoring it. And then I'll finish this off. Why do we care? Well, really, it's great because it's a great way to pass information through time, like legit, right? Like I can pass a message to you as the programmer in the 90s about something funny that happened that you have to deal with. And it allows us to deal with exceptional situations however we want, very clearly. Your normal operating code, and then your exceptional situation code. And it gives us that nice logical divide. Just like the file I/O stuff, the takeaway from this lecture is raise exceptions, accept how to raise them, how to deal with them. They exist. If you need them, you know that they exist and you can find out more.